This is A21, Module 4, January 2008, and this is question 4. Figure 4.1 illustrates apparatus that could be used to investigate oscillations. The signal generator varies the frequency of the oscillating piston. The piston causes the mass spring system to vibrate, and the displacement of the mass can be obtained from the pointer moving against the scale. So there you can see the pointer moving against the scale. So as this is moving up and down, the pointer moves up and down the scale. On figure 4.2, sketch a graph of the amplitude of the mass as indicated by the pointer in the scale against the result of dividing the natural frequency of the mass spring system by the driving frequency of the piston x-axis. So what you have to do is we want our graph which has got the peak in the middle, but the peak is going to happen at 1 because you know that you get the maximum amplitude whenever you have the natural frequency equal to the driving frequency, and so you're going to get your peak at 1 there, and they'll be looking for that. And so it's not going to start at 0 because the ratios are never not there. Okay, so you've got your nice peak at 1. The next part of the question says, what is the name given to describe the situation at which the maximum amplitude occurs? And the answer is, of course, resonance. The experiment is now repeated with a viscous damper in the form of a thick piece of card. The mass of the damper is negligible compared to the original mass. The new situation is as shown. Sketch a new graph to show the effect of the card on the oscillation of the mass spring system. Label this graph B. A mark will be deducted for not labelling this graph. Now this graph down here should have a wider frequency response, and we would have taught you that the maximum amplitude occurs at a slightly lower frequency. In this question they're suggesting in the mark scheme that that frequency is still the same, that you get the maximum amplitude, and it's a much wider. So I would have been inclined to move that peak over a wee bit, and in later mark schemes of 2010 they do move the peak over a wee bit to the left, but we'll just leave it the way it is because that's the way the mark scheme's looking for the marks. And of course label this graph B, and if you don't do that you lose marks, so I almost lost a mark there. The signal generator is switched off when the system in figure 4.3 is oscillating. On the graph axis of figure 4.4, sketch a graph to show the variation of amplitude of the damped oscillation with time after switching off. The time axis extends over a long time, and again I'm just going to make sure that my oscillations have a constant time period by marking on every couple of centimetres here. And of course we're going to show that the amplitude is getting less and less. No, in fact it's not displacement, it's amplitude, and therefore we don't need to worry about the constant time period. The amplitude is just getting less and less and less until it eventually end up at 0. And in the negative direction too, of course, like that. The system of an A is an example of a forced oscillation. Give another example of a forced oscillation. You should identify what is being forced to oscillate and what is the driving frequency. So the example I'm going to give is a person pushing a swing. So you get an example and learn it. The component being driven is the swing, and the component doing the driving is a person. And they're only giving marks for identifying these two here.